Okay, so this is the example we're going to try to cover first here for analyzing a truss. And what I've got here is just the loads broken down. Whatever your standard top chord loads would be broken down by the joint. So that's why the heel joint is half the load. Have you guys gone over truss loading and stuff like that at all? I guess you guys haven't had your structural design class yet? Okay. Okay. Standard truss loading. Just so you guys know, in my former life, I was a structural engineer, and I spent several years doing training for a couple of different truss companies. Standard truss loading is usually a 40, 10, 10. So the 40 and the 10 describe the top chord. 40 pounds is your live loads, which is your snow, water, wind, and so on. Your first 10 then is for the top chord. By top chord, of course, I'm talking about the top of the truss. That covers your materials, your sheeting, the wood on the top chord of the truss, shingles, tar paper, and all that. It actually usually allows for 2 layers of shingles on top of that. The third 10 is the bottom chord down here, which is just a dead load. They don't figure there's going to be too much snow getting on that, hopefully. On that 10 pounds is the weight of the bottom chord, sheetrock, insulation, and any mechanicals like ductwork or electrical and anything like that that might be going through the top chord. It's a little more complex than that. Now current codes require that they design for what they call a 30-pound roving or 300-pound roving construction load. That's somebody like me climbing around up there getting everything tied together as you're building it so that it doesn't collapse if you get too much equipment in one spot where you're building it, or if you have a pallet of shingles dropped on it or whatever, when you do the roofing, that's not going to collapse under that. But anyway, what we're going to do here is we're just going to look at top chord loads. And we've divided it up, rather than having it continuous, basically the top chord load would be done as so many pounds per square foot, and then you adjust that for the truss spacing to pounds per linear foot of the truss. We're just saying we're going to gather up those loads and we're going to concentrate them at the joints. And the method of joints is generally the preferred method of analyzing a truss. So we're going to start at one of the heel joints, and actually the first step we have to do is to find the reaction loads. This one's relatively simple because it's symmetrical, or at least pretend it's symmetrical. My artwork really sucks, so we'll get used to that. So the reactions here are just going to be the total load divided by 2. Half goes to each reaction. So you're going to have the 300 plus 600 plus 600 plus 600 plus 300 divided by 2. Does that give us 2,400 total? So 1,200 pounds to each reaction. So here we have basically 4 joints we have to analyze. The heel joint here, those 2, and then the peak. Because the other side is going to be symmetrical, those should be the same. So we'll start out with the heel joint down here. I did not notice I gave you the angles on these 2 webs, but I did not give you the angle here. We just gave you that it is a 612 slope. So I'll call that joint A. So what we know about joint A is there's 300 pounds coming down, and there's 1,200 pounds going up at that joint. The angle here can be found. Inverse tangent is 6/12. So I'm going to start out. Anybody have any questions on the trig for the angle using the inverse? We're all good with that? Inverse tangent is 6/12. Should be 2656. Yep, 2657. So 26.57 degrees. Next question. Does anybody have any questions as to where I got this little diagram here? All I did is I just took basically this little section of the truss and I blew it up. The 300 pounds we know is coming down because it's a load. The 1,200 pound reaction we know is pushing up because it's a reaction. It has to oppose the loads. So now we just have to balance out our forces with the other 2 members of the truss. we have the top chord and the bottom chord coming in here. The two equations we have to worry about are the sum of the vertical forces, FV stands for forces in the vertical direction, has to equal 0, and the sum of the horizontal forces has to equal 0. So we're going to start out with that sum of the vertical forces. Now to do that, we have to break down what we have for vertical and horizontal forces. Right now, let's see, I'm going to use light brown for vertical. We have the 300 that's vertical. That's actually going to be negative 300 because it's pointing down. We have the 1200 that's obviously vertical. That'll be a positive 1200 going up. We don't have anything else that goes strictly up or down, but we do have members that go at an angle, so we have to break those down into components. So the top chord here has a horizontal, put that in a different color, has a horizontal component and a vertical component. So if I call that member there, I want to get my letters straight here. How did you guys do your section of joints? Did you label each piece of the truss with a letter, or what did you guys do to label them?
We did like, if you have A at the bottom, and then the next point's B, we did force AB, remember AB.
Okay, so this was joint A. You guys labeled them as joint B, C, D like that. So this up here was AB. Okay, I just want to be consistent. So this is AB, we'll call it X for horizontal. This is ABY for vertical. So what's going to go on here? ABY, you notice I have it pushing down. And the reason I have it pushing down, we have to make an assumption here as to what direction this vector goes. And I'm saying it goes this way towards the joint because I have 300 down and 1200 up. The vertical component of this has to go down to balance that out. So it has to be a negative value. So the negative value of ABY. And that has to equal 0 because those are the only vertical forces or components of vertical components of force that we have here. So I'm going to pause for a second. Does everybody see where that came from? Okay. Horizontally then, we have, this is going to be force AC. I'm going to assume that that goes to the right. And I'm going to call the right side positive and the left side negative, just like on a number line. So AC is going to be positive. And the horizontal component of AB, so ABX is going to be negative because it goes to the left. Again, I picked AC to go to the right because I knew that ABX, if ABY was going to push down, ABX had to go to the left. Because if this vector, if AB goes like that, for this to go down, that has to go that way because it has to continue from tail to head of the vector. Does that make sense? Basically, all I'm doing is instead of going from here straight to here on the vector, I'm going the long way around. Okay, so now that we have these kind of generic equations out, let's fill them in with something usable. ABY is going to be found as a component of AB, and the component is going to be based on the 26.57 degree angle. If that's 26.57, since this is horizontal here, it's going to be parallel to this, so this angle here is also 26.57. So that means AB over here, or ABY, let me just expand this out. So this is AB. This is 26.57 degrees, ABX, ABY. My horizontal component is going to be the vector AB times the cosine of the angle. My vertical component will be the vector AB times the sine of the angle. Actually 5.7, not 5.6. So filling into these equations up here, for the vertical equation, I have 0 equals negative 300 plus 1200 minus AB sine 26.57. I'm going to go ahead and finish that off. I'm going to actually do the sine of 26.57. .447. So 0 equals negative, and I'm going to go ahead and combine my negative 300 and positive 1200. So it's 900 minus AB times 0.447. Since that one's solvable, it has a single variable in it, let's go ahead and just solve it. So we are going to subtract 900. Negative 900 equals negative, I'm going to rewrite this a little bit easier to read, 0.447 AB, and divide by my negative 0.447. I realize I left my negatives off, but we all know two negatives divide to make a positive. So we get 2013.42. That is AB. Okay, so I'm going to pause there. I took this equation that was my vertical equilibrium equation, and all I did was replace the negative ABY with, or just the ABY, I should say, with the sine function to get the component of AB for the vertical component. Any questions on that? Okay, so then just put in the value for the sine of 26.57 degrees. And since there was only the one variable, AB was the only variable there, I just solved the equation. So now we're going to jump to the horizontal equilibrium equation. 0 equals AC minus ABX but we don't know AC at all. We do know that ABX is going to be AB times the sine. And I'm going to put the sine in front here. Sine of 26.57 degrees, not sine, cosine. Should pay attention to what I'm doing. ABX is the horizontal, so that's cosine of 26.57 degrees times AB. So I'm going to fill in two things here now. AC we still don't know anything about. We can find the cosine of 26.57. Which is 0.894. We also know that AB is 2013.42 pounds. So my next step, I'm going to multiply 0.894 times 2013.42. So what that is telling me is the horizontal component of AB is 1,800 pounds. Any questions there so far? So to find AC, it's just a matter of solving this equation as well. We're adding 1,800 to both sides. 1,800 equals AC. So AC is 1,800 pounds. So back up here, we've got 2013.42, I believe. Yep. And here we've got 1,800. Before we go any further, we should ask, is this top chord here, is this in compression or tension? Careful. If it is pushing towards the joint, Remember, the arrows on these vectors are reactionary. So if that is that truss member is sitting there, if it is pushing towards the joint, that means it is pushing out. It's not being pulled out. The member itself is pushing out. So if you think of like a piece of foam rubber or a spring, if you push in on the spring, it's going to push back out. So for it to be pushing out, it must be compressed. So it is in compression. So I'm going to label that with a C for compression. The 1800 is pulling away from the joint. And again, if that's a spring, in order to be pulling in away from the joints, it must be stretched or it must be in tension so that it can pull back in. So that is 1,800 pounds in tension. So do we have any questions on the heel joint? Would you rather I keep going with this example, or would you rather I give you another example to look at quick so you can try to do the heel joint? Try it on your own.
Can you just do B and that? B, like B to C?
Okay, we'll do B and C.
Oh, no, I don't want to have to do that. And that's just regular trig, isn't it?
Well, it's going to be systems of trig equations. Let's go ahead and do joint B quick. So joint B, we have 600 pounds coming down on it. This is at an angle of 50 degrees. This is at an angle of 26.57 degrees here. And we know that this was 2,013.42 pounds. It's in compression, which means it's going to push out at both ends. So it's going to be towards the joint. The key to that is if that member is pushing towards the joint here, it's going to push towards the joint there. So as it's kind of counterintuitive with vectors, you're used to a vector always goes the same direction. But remember, we're looking at how that member is reacting to the rest of the truss. It's compressed, so it's pushing out on both ends. 2013, not 14. It is 13. Okay. So 2013.42. And so far, that's all the information we have. But we did have this broke down into horizontal and vertical components. And that's more important to us than the 2013.42 right now. So the 2013.42 is broken down. We had a vertical component here. The AB sine came out to be, I guess I didn't actually figure that out, was equal to 900 pounds technically. Which makes sense. It's just the difference between the 1,200 pound reaction and the 300 pound load at that joint. And the horizontal has to be 1,800 pounds. So that's just coming back from this previous example where we found the vertical, or the horizontal is this component, 1,800 pounds. And if I multiplied this out for the vertical, if I did 0.447 times 2013.42, I would get 900 pounds. So we have those components coming in, but we're also going to have these components here, a horizontal and vertical component there. What was that, D at the peak? Yeah, D and C. Sorry for all the scrolling there. So we've got D here and C. So this is going to be, so this is going to be BDX and BDY. This angle here is still my 26.57. I'll do the same here. This is going to be BCX and BCY. And again, that angle is 50 degrees. So let's just do the trig on each of these. BDY is going to equal BD times the sine of 26.57 degrees. BDX is going to be BD times the cosine of 26.57 degrees. So I'll pause there. You guys all remember how to find your vector components? Does that look familiar? Okay. So we'll do the same for BC down here. BCX is going to be BC times the cosine 50 degrees, and BCY is going to be BC times the sine of 50 degrees. I know I just had these, but we'll find them again. Cosine of 26.57 is 0.894. Sine was, what, 0.447? Then we got to do cosine for 50 degrees. 0.643. And sine for 50 degrees. 0.776. Sorry, 0.766. So now let's look at our equilibrium equations. Let's just look at the sum of the vertical forces. I'm going to start out with known forces. The 600 pounds goes down, so that's a negative 600 pounds. The 900 pound component here goes up, so it's a positive 900 pounds. The way I have it drawn here, I have this top chord's almost always in compression, so I drew that in compression. If this one's in compression, this one's most likely going to be in compression. On this web here, I just took a guess that that was going to be in compression. I don't know yet. So if I get an answer that is negative for BC, I know that it wasn't in compression, it was in tension. So I just have to switch that at the end. So we're going to assume BDY is negative, is going to go down, so minus BDY. We'll put the value in for that in a little bit. And then BCY, we're assuming goes up, so plus BCY. So let's fill in everything we can for this equation. And of course, that has to equal 0. So 0 pounds equals, I'm going to combine my negative 600 and my 900 to get positive 300. Minus BDY. I'm going to put in 0.447, that's sine, times BD. Plus BCY, 0.766 times BC. So any questions on getting things substituted into that equation? Okay. The only change I will make to this equation is to do a little bit of rearranging, and we'll do that in just a little bit. But for now, that's going to be one of the equations in our systems of equations. So next, look at the sum of the horizontal forces. The only known force we have is the 1800, and that is going left to right, so that's in the positive direction. We have BDX, which is going right to left, so that's negative direction, so a negative BDX. BCX is also in the negative direction, so negative BCX, and that has to equal 0. So again, we have 0 equals 1800 minus BDX, right here is 0.894 BD. And BCX, right here, is 0.643 BC. So that is my second equilibrium equation. Any questions on how I got the number substituted into that? Good? So now we've got to solve this system. As I rearrange it, I'm going to take this equation here first. This is my vertical equation. And I am going to move the 300 over to the other side. So I'm just basically subtracting 300 from both sides. So I have negative 300. I'll put an arrow here instead of an equals. Negative 300 equals negative 0.447 BD plus 0.766 BC. I'll do the same thing down here. So I have a negative 1800 Again, I just subtracted 1800 from both sides. Equals negative 0.894 BD and negative 0.643 BC. So I have a system of equations. How much experience do you guys have solving systems of equations? Okay, what's that?
Put it in Wolfram.
Put it in Wolfram. You can do matrices if you have a TI-84 graphing calculator, 83. It goes in there pretty well. We're going to solve this one brute force, just because it's not as hard as it looks. I prefer to use the elimination method, or sometimes called the addition method. So I need one that has a positive value or one that has a negative value, or I can force them to one be positive and one be negative. But the way I'm going to do this, I'm going to get rid of BC. So I need those to both have the same coefficient, just one positive, one negative. Since it has really ugly decimals here, finding the number to multiply them by to make them the same is going to be really difficult to do. What you often don't see in a math class is you don't have to multiply every number by the same thing. You can divide every piece of the equation by the same thing. So this equation here, what I'm actually going to do is I'm going to divide it by 0.766. By dividing by 0.766, it's going to make this here positive 1 BC. So negative 300 divided by 0.766. Negative 391.64. Negative 0.447 divided by 0.766 is a negative 0.584 BD. So that's my top equation. My bottom equation, I have to do a similar thing. I have to make this equal 1, but negative 1 is what I want it to be. So I'm going to divide that by 0.643. So now when I divide that by 0.643, that'll be a negative 1 BC. So now I've got the negative 1800 divided by 0.643. Negative 2799.38 equals, and then I have a negative 0.854 divided by 0.643. 584? Did I write that down wrong?
No, you had it written down, right?
I just typed it in wrong? Okay. Oh, 584. Wow. No, it's this one up here. Sorry. This is the one I'm actually taking. 854.
Oh, yeah.
Okay, I was going to say. I didn't think I was that bad today. But it should be divided, not subtracted. So yeah, negative 0.854 from up here divided by the 0.643. So I get a negative 1.328 BD. You guys remember the elimination method at all? Sometimes called the addition method. Okay. So we're going to add the columns. Here we're going to get 31, sorry. Negative 3191.02. Let's see here. Negative 1.912 BD, and positive 1 and negative 1 BC cancel out. So to solve for BD, it's just going to be dividing by negative 1.912. So we got 3191.02 divided by negative 1.912. So 1668.94. That is BD. So I'm going to scroll all the way back up to my original diagram. So BD here is 1668.94. Now I made the assumption in my original diagram that was pushing towards the joint, and I came up with a positive answer. So that tells me that assumption is correct. So that is in compression.
So is it, if you have a positive number, it's always going to be compression, and negative number will always be tension?
Not necessarily. A positive number will mean my assumption was true. A negative number will mean it's the opposite of my assumption. In my original diagram for this, I had that pointing this way because the two vectors went left and down. So I had it pointing that direction, and since I got a positive result, that assumption was true. This one here was pointing this direction, so if I get a positive result, that assumption is true. If I get a negative result, it means it was going the other way. So we still have to solve for BC. So it doesn't matter which equation we use here. I'm going to take this top one since we did all the work to get it. And we're going to plug in. So I'm going to put it right over here. Negative 391.64 equals negative 0.584 times, I'm going to run out of room there, 1668.94 plus BC. So to solve for BC, sorry about my getting crowded there. I have to multiply these together first. So the negative 391.64 isn't going to change. I'm going to take my negative 0.584 times 1668.94 and get negative 974.66 plus BC. I dropped the 1 off the BC. And now we're going to add the 974.66. So we have 974.66 added to our negative 391.64. Oops, that didn't come out right. 64. There we go. So that gives us 391. That didn't work. Try it again. So negative 391.64 plus 974.66. 583.02. So that's saying BC is 583.02 pounds. I got a positive result, which is telling me my assumption was true. I had assumed that it was pointing towards the joint, so that it was in compression. So it is in compression. So 583.02. That is compression. So any questions on that one? That's probably the most difficult joint of the truss because you have to get into the system of equations. Joint C is actually considered, what's that?
Well, pretty much after you find A and B, it's easy to find the rest.
Yeah, let's do C quick because C isn't too bad, but it does still have to deal with the equilibrium equations. So we've got 1800. Let's draw that one out quick. Since we made it this far, it won't take long to do C. Now that was in tension, so that's 1,800 pounds in tension going away from C. This one we don't know yet. This was compression, so that's going towards C. About 583.02. That was B, this was A. So this is going up to D. We have no idea whether D is in compression or tension, so we're going to have to guess. I'm going to guess tension. The reason why is, well, these two down here are horizontal. They can't have any vertical components. This one's going to have a vertical component that pushes down because it's in compression. So I'm guessing this one's in tension, so I get a counteracting vertical component. Actually, you know what? Let's do this. Let's guess that one is in compression too, just for fun. We're going to guess this one in tension just because it's a bottom chord, and a bottom chord is almost always in tension. what was that, point E over there? I didn't label that side, did I? We're going to call it point E then. So we'll call this E. So we had our breakdown here. This was going to be horizontal and vertical like that. I'm just going to pull these down here again. Oops. Joys of technology, huh? Might have been quicker just to recalculate them. So anyway, we have here, the horizontal here is 0.643 BC. The vertical here is, oops, I didn't get the sign of 50. 0.766 BC. For DC over here, I'm going to do it on this side just to have a little more room. You know, this is 60 degrees. So this here, we'll put it over here. DCY is going to be sine of 60 times DC. Sine of 60 is 0.866. 0.866 DC. DCX is down here. That's going to be cosine of 60 times DC. So that's going to be 0.5 DC. So I'll put those in. This is 0.866 DC. This is 0.5 DC. So any questions on setting up that joint so far? Okay. So then for my equilibrium equations, my vertical equilibrium, I have 0.766 BC, but I know BC was 583.02. That's going down, so I'm going to make that negative. And this one's also going down the way I have it drawn, so that's also negative. So 0.866 DC, and that has to add up to 0. So to simplify that, I'm going to combine the negative 0.766 times 583.02, negative 446.59 equals 0 minus 0.866 DC. So there's my first equilibrium equation. There's my vertical equilibrium equation. For my horizontal equilibrium, I have the 1800 is going the negative direction. I have BC is going positive direction, so 0.643. And we know BC is 583.02. DC is going in the negative direction, so a negative 0.5 DC. And CE here is going in the positive direction, so plus CE. So, and of course that equals 0. So for that equation, 0 equals, I'm going to go ahead and combine these right here. So that's a negative 1800 plus 0.643 times 583.02. So that's a negative 1425.12. And a negative 0.5 DC plus CE. So that's my horizontal equation. Now for my vertical equation right now up here, there's only one variable, so I can actually solve that to get DC. So 0 equals negative 446.59 minus 0.866 DC. We divide by, or sorry, before we divide, we got to add the 446.59. So 446.59 equals a negative 0.866 DC. Dividing by the negative 0.866. So divided by negative 0.866, we got a negative 515.69 equals DC. So that's telling us is our assumption that that was in compression is wrong. It's in tension. Now the part that a lot of people mess up, even though we've proved that our assumption was wrong, we have to keep that as negative for right now when we substitute it back into the horizontal equation to find CE. So we'd have to substitute back up into here, replacing DC with a negative 515.69. So that's going to be 0 equals the negative 1425.12 minus 0.5 times a negative 515.69 plus CE. And of course, at that point, you can solve that for CE. So back up here, all the way up to the top. This is 515.69. That's in tension, so it's pulling away from the joint. I didn't find CE, but it's just a simple equation for you guys to solve, and we have like 2 minutes left. So any questions you guys want me to go over? Okay.